Hello everyone, myself Soumya Hulswar, B.Ed first year student teacher of KLE Society's College of Education, Ankola. So here I introduce you to magnetic effects of electric current, class 10 science. Before we proceed to this lesson, let's perform a small experiment. Just take a magnetic compass and place it over a current carrying wire. What do we observe? We see a deflection in the magnetic compass. What does this mean? A magnetic compass shows deflection only in presence of a magnetic field. In this experiment, we saw a deflection in our compass. This means that a current carrying wire produces a magnetic field. Thus, there is a link between electricity and magnetism. The experiment we did was actually done by a Oersted in 19th century, where he established a link between electricity and magnetism. Let's study the properties of bar magnet. If a freely suspend bar magnet, the end which point towards the north is a north-seeking end, and the which point towards the south is a south-seeking end. Therefore, a bar magnet has a north pole and a south pole. Through various activities, we have observed that like poles repel while unlike poles of magnets attract each other. Let us do one more experiment. Take a bar magnet, fix it on a sheet of paper. Next, sprinkle iron filings all around the magnet and gently tap the paper. Then we observe the iron filings, which were randomly spread around the magnet, have aligned themselves into a specific pattern. This means a magnet exerts an influence all its surrounding region. The iron pilings must have experienced a force that has arranged them in such a pattern. The lines along which the iron pilings are arranged is nothing but the magnetic field lines of a bar magnet. The region surrounding the magnet in which the force of the magnet can be felt is the extent of the magnetic field of that particular magnet. Magnetic field is a vector quantity that it has a both magnitude and direction. Thus, we can say that the magnetic field lines of a closed curve, if the field lines are really closed, it indicates a strong magnetic field. On the other hand, if the field lines are far apart, it indicates a weaker field. Also, magnetic field lines can never intersect each other. Next concept is magnetic field due to a current carrying conductor. The magnetic field on a particular point depends first on the location of the point from the conductor, and second one is direction of current in the conductor. Let's see the magnetic field due to a current through a straight conductor. Straight conductor. We have to find magnetic field around this wire. We had connected to a battery to flow the current. So now we know that how to find the magnetic field in this conductor. We had studied about right hand thumb rule. We says that we have to find the magnetic field at any point of the conductor. Then we have to hold in such a way that the thumb points in the direction of a current. Then the curling of fingers will give you the direction of magnetic field. If we look at this conductor, the current will be flowing in upward direction. When we switch on the battery, let's hold it in a right hand, so a thumb will point in upward direction. And when we curl the fingers, you will find out that the magnetic field will be in circular in shape. You will find that there will be some concentric circles formed around thin wire, and direction of these circles is given by curling of the finger. So its directions can be found out easily by using right hand thumb rule. Now the strength of this magnetic field also depends on some factors. If we increase the amount of a current through this conductor, the magnetic field increases. And we had seen in Oersted experiment also that if we move away from it wire, the strength of the magnetic field decreases. So we can say that the strength of magnetic field due to the straight current carrying conductor depends on two factors. First is it is depends directly upon the current in the wire. Secondly, It is depends on the distance of the point from the conductor. It decreases as the distance increases. So we will say that it is inversely proportional to the distance of the point from the wire. Next concept is magnetic field due to a current through a circular loop. Let us bend this wire in the form of a circular loop and try to find out that the magnetic field pattern due to this loop. We have learned that the magnitude of magnetic field depends inversely on distance, and the concentric circles representing magnetic field get bigger and bigger as we move away from the wire. As we move at the center of the loop, the arcs due to concentric circles would appear as straight lines. Every section of the loop would contribute to the magnetic field appearing a straight line at the center of the loop. By applying the right hand thumb rule, we see at every section of the wire contributes to the magnetic field in the same direction within the loop. Also, a convenient way to find out the magnetic field due to a loop is rotate our fingers in the direction of current flowing in a loop, where our thumb points in the direction of magnetic field. If the current flowing in the loops is in the anticlockwise direction, the magnetic field points in an upward direction. But the current flowing in the loops is in a clockwise direction, then the magnetic field points in the downward direction. We have also learned that magnetic field due to a current carrying conductors depends on a magnetic field. If a circular coil has n turns, then magnetic field produced will be n times of that produced by a single turn coil. Next concept is electric motor. An electric motor is a rotating device that converts electrical energy into mechanical energy, and electric motor is used as an important component in electric fans, refrigerators, mixers, washing machines, computers, MP3 players, etc. Let's discuss about the electromagnetic induction. The production of electricity from magnetism is called electromagnetic induction, or we can also define it as a changing magnetic field in a conductor includes a current in another conductor is called electromagnetic induction. In this figure, moving a magnet towards a coil sets up a current in the coil circuit as indicated by deflection in the galvanometer needle. Next, what is galvanometer? Galvanometer is an instrument that can detect the presence of current in a circuit. Electric generator. This is a figure of electric generator. Electric generators works on the principle of electromagnetic induction. These are the device where mechanical energy is used to rotate a conductor in a magnetic field to produce a electrical energy. There are two types of electric generators. First one is AC electric generator. Second one is DC electric generator, where AC stands for alternating current and DC stands for direct current. The last concept of this lesson, that is domestic electric circuits. In our homes, we receive supply of electric power through a main supply, also called mains. One of the wire in this supply, usually with red insulation cover, is called positive wire, and another wire with black insulation is called neutral wire or negative wire. In our country, the potential difference between the two is 220 volt. Often, two separate circuits are used, one of the 15 ampere current rating for appliances with high power ratings such as geysers, air coolers, etc. And the other circuit is of 5 ampere current rating for bulbs, fans, etc. As safety measure to avoid electric shock, will in contact with the appliances with metallic bodies like electric press, toaster, table fan, etc. We use the earth wire, which has an insulator of green color, and it is usually connected to metal plate deep in the earth near the house. The metallic body connect in the earth wire provides a low resistance path for the flow of current. Thus, it ensures that any leakage of current to the metallic body of the appliances keeps its potential to that of the earth, and the user may not get a severe electric shock. Thanks for watching this video.